Hello everyone. In today's session, we are going to discuss the relationship between PCP, Post Correspondence Problem, Modified Post Correspondence Problem, and Turing Machine. Okay, so we'll be using a lot of conversions. Like we have a conversion from PCP to Turing Machine to PCP and PCP to MPCP and all. Okay, so why we need all this, and what is the relationship between this PCP, MPCP, and Turing Machine? So first, I'll start with what is Post Correspondence Problem. PCP is Post Correspondence Problem. This is a normal puzzle problem. Okay, so puzzle problem which has some set of dominoes like this. Okay, like I'll take one example. This is one domino. So dominoes, like this is one single set, we call it as a domino. So we have three dominoes here, 1, 2, 3. Either it is expressed in this pattern, or there are multiple ways where this dominoes can be expressed. One way of representation is using this dominoes. Another, I can use a set like this. I can have two sets. One set consists of the first string BAB and ABC. So this is your first one, second one, and third one. And B consists of the denominators like AB, ABA, and BC. Okay, either expressed in the list structure like this, or can also be expressed in terms of your table structure like this. I have AB, and you have three strings. Okay, A list consists of all the numerator like A, BAB, and ABC. It is in pair. Okay, so corresponding B pair is AB. This is your denominator, ABA and BC. Okay, there are three ways in which this post correspondence problem can be expressed, either in set of all dominoes, or in terms of this list structure like this, or we can have a structure like this. Okay, now the actual goal here is to arrange this domino such that the string that is formed by the numerator should be equal to the string that is formed by the denominator. I'll give you a solution for this problem. Okay, I have taken a very simple problem. So start with this domino AAB. Okay, now I have A in both numerator and denominator, and here I have an extra B. So in order to match this B, I should have a domino that starts with B at top. Okay, and the domino that starts with B at top is this one, BAB and ABA. I think I have taken a domino that already matches. It's okay, no problem. So this B matches, and this A matches, this B matches. Now I have extra A at the bottom. So I have to choose another domino like ABC and BC. Okay, so this A matches, BB, CC. Okay, now combine all the strings of numerator. I have this numerator as A, BAB, ABC, and the denominator I have AB, ABA, and BC. Okay, see, the string formed by the numerator and the string formed by the denominator are same. Okay, so this is the solution. Okay, so here the solution is, this is your first domino, and this is your second domino and third domino. By arranging it in this pattern of 1, 2, 3, I got a solution for it. Okay, this is very simple example I have taken. Sometimes you can, sometimes we need to reuse the same dominoes too. It is also allowed. A domino can be used any number of times. Okay, and the problem here is, sometimes when you are finding a solution for these kind of puzzle problem, it will enter into a looping pattern. Okay, you might not have a solution to, but there is no official procedure to prove that we don't have a solution for it. Okay, it is like writing a program with the infinite loop. We don't have any predictions that can be done priorly if the input is based on the user. Okay, see, if input is taken from the user, and you write a for loop based on the input given by the user, and based on the conditions, it might enter into an infinite loop too, right? Similar condition exists for this domino arrangement too. Sometimes you might not have a solution, and you don't have a stopping criteria too. Okay, we'll be keep on using it, and it might enter into a looping structure. So this process, like when you don't have a solution, it might enter into a looping structure, right? So this is called undecidability. Okay, so we cannot decide whether the domino, the PCP problem will have a solution or not. Okay, so this problem is called, like we have to prove this, like there is no official procedure to directly take this problem and prove it. Okay, and how can we prove it is, like to prove this PCP is undecidable, we are using this Turing machine problem. Okay, since we already know that the acceptance of Turing machine is undecidable, we are going to convert this Turing machine problem to PCP and prove that if a Turing machine can be simulated using a PCP problem, then if Turing machine is undecidable, then PCP is also undecidable. Okay, that is how we are relating Turing machine to this PCP problem. Okay, in order to prove that PCP is undecidable, since we already know that the acceptance of Turing machine is also undecidable, we are going to convert Turing machine problem to PCP. And if there exists a way to convert a Turing machine problem as a PCP problem, then we can say that this is undecidable, hence this is also undecidable. Okay, but we cannot directly convert a Turing machine problem to a PCP problem, so we are going to convert into a modified version of PCP. Okay, modified version of PCP is very simple. It is going to start that the first domino, the first element should be a matching domino. Okay, in this problem we use the symbol # to start the process. Okay, the first element of the domino should be a matching domino. That is the difference between PCP and MPCP. PCP is something like we can have any combination of it. There is no rule that the first domino that you take should have a matching element. Sometimes it matches, sometimes it doesn't matches. We can have this as a first domino too. It is also allowed. Okay, so what we are going to convert that is like the modified version of PCP says that the starting domino should be a matching domino. Okay, so we can convert a Turing machine problem to a modified version of PCP, and we can prove that if you are able to simulate a Turing machine as a PCP problem, we are going to say that PCP is also undecidable. Okay, and since it is a modified version of PCP, how we are going to relate PCP to MPCP? So that's the problem. So we have a conversion procedure to say that this MPCP is PCP again. Okay, so there is a rule or a way to convert all MPCP to PCP. Okay, so that is how the relationship exists between PCP, Turing machine and MPCP, modified version of PCP. Okay, since post correspondence problem is undecidable, to prove that it is undecidable, we are going to convert a Turing machine problem to a post correspondence problem and say that since Turing machine problem acceptance is undecidable, hence PCP is also undecidable, but we don't have a direct conversion. So what you're going to do is, we are going to convert Turing machine to PCP, and there is a procedure to convert MPCP to PCP. Okay, so with this relationship, we can say that PCP is undecidable. So in the next video, I'll show all the remaining things. Okay, the conversions, how to convert a post correspondence problem, a modified post correspondence to problem to a PCP, and Turing machine to a modified post correspondence problem. Okay, thank you.